Hello, everybody. Welcome to the fourth session of this second seminar webinar series, The Importance of Being H.P.C. Earnest. This is a series that here we've organized at CCAM, motivated by the impact that H.P.C. has on simulation and modeling. In each of these sessions, we invite leaders of collective initiatives in Europe and the USA to focus on challenges of the development of scientific codes, algorithms, data-driven initiatives in the context of future H.P.C. landscape. And we do that, organize them in the CCAM spirit. And therefore, we try to bring together complementary initiatives that focus on the science that is made possible by combining modeling methods with optimal exploitation of H.P.C. resources. We do that with the aim of having a dynamic session to bring and ensure that we have discussions in a set of presentations that are dealing or touching different areas of interest for the CCAM community, so creating an interdisciplinary environment. Today's session will be shared by Sarah Morena, CCAM Deputy Director, and myself, and it's a pleasure to have two very distinguished lecturers. We had planned, as you had seen in the announcements, 3, but unfortunately, due to a last-minute problem, Elisa Molinari has been unable to attend. So we will hold today the event with these 2 lectures plus the common discussion session as we always do. So today we have with us Edouard Audit, who is an expert in numerical astrophysics. He was one of the founders of Maison de la Simulation in Saclay, and he's also currently the coordinator of the EOCOE, that's an energy-oriented center of excellence. We have had in previous sessions other centers of excellence. This is a EU initiative to develop the software and bring the communities to exploit the future exascale supercomputing hardware that will be implemented in the near future. And this COE, EOCOE stands for energy oriented. So the objective of this center of excellence is to develop and apply cutting edge computational methods to accelerate the transition towards production, storage, and management of clean energy. I'm sure we will hear about it in the coming lecture. And the second lecturer is Gianluca Palermo, who is associate now professor in the Politecnico di Milano. He has an education as an engineer, and he has an interesting background because he has been working both in the industry as a consultant engineer and in the academia, earlier in the Università della Svizzera in Lugano, and now in the Politecnico di Milano. He is an expert in H.P.C. architectures and in the development of applications, and is here today also as the principal scientist of Politecnico Milano in exascale for COVID, which is a public-private consortium also funded by the Commission, in this case in the context of the fight to the COVID pandemic, and which has a strong computational component. And I'm sure we will also hear about that and all the science that is associated to this initiative. So without further delay, we will start. First speaker is Edouard Audit. So Edouard, please, now the floor is yours.
Thank you. Good afternoon, everyone, and thank you very much for inviting me to this webinar series. It's a pleasure. I thought I was supposed to share my screen, but it's not activated.
It's it. You don't have the green button in the middle of your screen saying share screen?
Oh, sorry. Yeah, I was looking at the...
No. So do you see in the bottom, there is a tab and there should be a green.
Yeah.
Ah, okay. Yes. Now we can see it. Yeah.
Can everyone see correctly?
Yes. Yeah.
Okay. Thank you. So I will present you as Ignacio mentioned, the energy-oriented Center of Excellence. So as was mentioned, ECO is one of the 9 Center of Excellence that were set up by the Commission. So most of them are thematic Center of Excellence. And the idea of this Center of Excellence is to promote the usage of H.P.C in a given field. And so our field is energy, as you will see. And so the Center of Excellence has several targets, but one of the main issues is really to develop software for the next generation of exascale system for a given community. So just a little of background. So ECO is interested in renewable energy. And as you can see on this graph, it's not really a graph, on this picture, renewable could easily power the world in principle. So I don't know if you see my mouse, but this little circle here is the world energy use. So the superficie of the circle is proportional to the energy. So basically, we need 16 terawatt per year globally. That's the energy that we use. The extremely large yellow or light green circle is what we receive from the sun. So it's 23,000. So it's orders of magnitude higher. And then all the other little dots or circle are other energy sources. We can note, and we are working that wind is between 25 and 70 terawatt per year that could be used for wind. It's a lot. And here on the right-hand side, you have the reserve in fossil energy or uranium that are not renewable. So you can see that if we could use efficiently a small fraction of geothermal, hydropower, and wind energy, we would really be able to provide the world with a clean and renewable energy. And so ECO is working in this context. I would say, so just another look at the energy sector. So here you have the evolution with time of the various sources of energy. So basically, we are now in 2020. So basically, in the middle of this graph, and this is a projection. And you can see basically, I don't want to go into the detail, but at the bottom of the chart, you have natural gas, coal, petroleum. So I would say old source of energy. And at the top, you have renewable energy, biogas, biomass, hydropower, things like that. And you can see, first of all, that the energy demand is predicted to be growing, and that the fossil energy are going down, as you can see here, and the share of renewable energy is constantly increasing with time. So the graph go up to 2050, so 30 years from now, where a majority of the energy should come from renewable energy. Now we have another transition. So I just discussed very briefly the energy transition. And now, as most of you likely know, H.P.C is also undergoing a major change with the upcoming generation of so-called exascale system, with the first system appear about now. So to go forward, you need a 100-fold reduction in energy consumption, I would say, from older generation of hardware to have machines that are tractable in terms of energy consumption. You need computing model capable of using tens of millions of computing elements. So that's really extreme parallelism. So computing element is a bit harsh to define nowadays. But if you take now the first machine at the top 500, the Fugaku computer, it has close, I think it's a bit more than 7 million computing cores. So you're within and it's only half an exaflop, so you're in the 10 million computing element. And if you take GPU, you have less GPU, but then you need to fragment your computation into very small parts to use the GPU. So then the number of computing elements can be extremely large. And you also have an issue with the architecture, which are now becoming a very heterogeneous, both the computing part and also the memory and the I/O system with a deep memory hierarchy and probably various I/O systems. So of course, this exascale transition will also require radical innovation and change in computing technology, and especially in the software that are developed to use this system. So that was a bit of background. And so ECHO is sitting there, and the objective is to use the extreme computing power offered by this new generation of computer to foster and accelerate the European transition to a low carbon and reliable energy supply. And so ECHO is at the crossroad of the two revolutions that I very briefly presented. So the energy revolution and the numerical of H.P.C revolution. So I would say the fundamental of the project is that we believe, and I mean, many people believe that the revolution in our technology will call also a revolution in the way application code are designed. So there is a huge amount of work to really modify a large legacy code to be able to use extremely large system. Our project is focusing on only 5 energy fields. So energy is an extremely wide topics, and you have many ways possible of producing renewable energy. I have shown in the beginning, and production is not only, then you might need to store energy and also to distribute energy. So all these are extremely important and difficult challenge. And for the moment, we are only focusing on 5 topical areas, which are wind for energy, meteo for energy, material for energy, water for energy, and fusion for energy. So wind for energy is really, I will give more example later, the optimization and the modelization of wind over complex terrain to optimize the placement of a windmill and the optimization of a windmill. Meteo is a very short-term ensemble run of a weather forecast. So when I say short-term, it's between a few tens of minutes to a few hours, maybe a day, but actually less than a day. So these are extremely useful to predict the production of a power of a solar cells plant or a windmill. To couple them efficiently to the grid, and also to make prediction. And one of the main areas is to make prediction of a rare event, very high production or very low production that could provoke a breakdown in the electric network. Material for energy, we are mainly working on solar cells and supercapacitors. And that we are doing, of course, in close collaboration with people of SECAM and also with other centers of excellence working in material. The water aspect has 2 things. One is hydroelectricity, so trying to predict the production of hydroelectricity, especially in the northern part of Italy, and also to assess the impact of climate change on these hydropower resources. And the other aspect, a bit different of water for energy, is geothermal energy and the modeling of geothermal reservoir and geothermal use. And fusion for energy is linked, of course, to the ITER project and to the production of energy using fusion in a tokamak plasma. So that is our 5, I would say physical topics. And the project is organized around a 4 exascale technical challenge that we believe are key issues for our application, but also more generally for exascale computing. So we have a scalable solvers, so linear algebra at the exascale, programming model, I/O and data flow, and ensemble run. So that is the 4 building blocks, or most key building blocks of our applications. So just because I think it's very meaningful, the structure of the project. So ECHO was part of the first round of Center of Excellence, and it was at first a 3-year project, and then we were continued for another 3 years. So that is the structure of the first phase of the project. So the colored vertical bar were our work package. So for Meteo, material, water, and fusion. So that was the project was organized within a topical physical work package, and we had this dark gray box at the bottom. Was work package 1, which was dealing with everything for advanced math, linear algebra, all the H.P.C. and technical aspect was gathered here. And so we worked like that for the first phase of the project. And then when building up the second phase of the project, we had a lot of discussion if we should or not keep the same structure. And we kind of shifted the project. And now the work package are really oriented toward the exascale challenge, because we believe now that the main goal of the project is really to develop application for exascale system, and that we need to be focused on technical problem. And so the work package are centered around the technical problem, and there is one work package gathering all the physical challenge. So we have these 4 technical work package that I will try to describe in more detail, which are a key bottleneck and key issue to work on the codes of all our scientific work package. And of course, as all Center of Excellence, we are closely linked to the I would say to the H.P.C landscape in Europe, so to PRESS, to Euro H.P.C, to the European Technology for H.P.C, to the extreme scale demonstrators. So I think it's standard. And one thing I will say a few words, we're also very linked to EERA. So it's the European Energy Research Alliance, which is more specific to us. So one danger of this structure is that we need to make sure that all the H.P.C and computer science development made in the work package are really useful and brought to the application. I forgot to say it, but in ECHO, we are only working on a production application. We don't do, I would say, mini apps or things like that. We are really trying to bring the software to a high level of performance, but production software that can be used by the scientific community. So just a few words about the management structure. So don't look at anything but the red ellipse on the right-hand side. So in order to ensure that all the technical work package are really working together and to build application, we have what we call an exascale co-design group. So we have regular meeting of people managing the application software and people dealing with a technical challenge, and to make sure we work in the right direction, that the tool developed can be really incorporated in real application, and that we are really working together to build up this exascale application. So this is something new to the second phase of the project. And so this group tried to monitor application progress toward exascale, initiate cooperation between work package for mission critical application design to make sure all the building blocks are compatible and are working well together, and that we have all the building blocks to work on the application. And really to have a tight collaboration between scientific challenge and technical work package. So it's really a critical issue and a critical part of the project to have this discussion between H.P.C people and people more on the physics side. So for example, you see here one slide from the work done by this exascale co-design group. So on this graph here, I won't detail, but you have I would say the model physical maturity. So physicists try to put more physics into the model, because with larger computer, you can do more physics. And on the vertical axis, you have the performance. And we try to design a path where we want more physics and more performance. And most of the time when physicists add new physics, the performance is at best horizontal. Probably the line would go down in many cases. And then you have the work of various work packages with trying to bring the performance up. And on the left, I don't want to go into the detail, but we had to switch from one code for solar cell study, PV-NeGES, to LibNeGEF, both for human reason and for technical reason, because we believe the new code will be more efficient, more easy to couple to other code, and more easy to bring to exascale. So this is a view of the project with all the partners. So we have a large number of partners. So vertically, you have all the physical challenge. The name here, and you will see them later as the name. So for each physical challenge, we have what we call the flagship application, which are those are supposed to be brought to exascale. And we have also, but they are not written here, a companion code, which are very useful for the physics and to reach our physical objective, but they are not meant to reach exascale. And so you have strong collaboration between I would say, this vertical scientific challenge and all the work package. So the objective of the project, of course, is to enable transformational energy science breakthrough in the sector that we are working on. And we will do that by redefining and promoting a few flagship applications. We want also, so we are also working on a computational method and H.P.C software that is a product of our horizontal technical work package, which are both dealing with H.P.C aspect, and you will see with also the data generated. I will skip that. So just before I go into more technical aspect, a bit if you want to follow us. So of course we have a website. We have a LinkedIn profile. We are also doing quite a few webinars, and we announce them on LinkedIn. And also we have mailing list. If you want to subscribe, you can write to me. And we have a YouTube channel also, ECHO. So if you're interested in a specific topics or in H.P.C aspect, you can also check there. And one last thing before I enter a technical aspect of the project is that now we are really trying to join the European Energy Research Alliance, which gather several hundreds of, I would say, SMEs, industries, and research and lab and university across Europe. And it tries to promote sustainable energy research within Europe. And so ERA is organized into a joint program. All the ERA joint program were on a dedicated energy topics. For example, they have a joint program on wind for energy. They have a joint program on material. And we have been pushing the creation of a transversal joint program, which is called a digitalization for energy, to promote H.P.C, but it has a bit of a wider scope, but also data technology for energy. And this, so it was a long endeavor, and this horizontal joint program has been approved by ERA. So we really will be able to work in close collaboration with ERA and try to have more impact at wide in the energy sector, promoting H.P.C technology. So this is the project. So you recognize the vertical green bar are our energy science challenge, and horizontally you have our technical challenge. So we have identified, you see the dots, and the larger the dots, the more work needed. So so most of the code, except maybe one, need linear algebra at various degrees of importance. For all the code, we have a new programming model, and we need to really reshape the code and use more modern programming technique to reach exascale. Many codes have I/O issue, and some of them, not all, need ensemble runs to reach the scientific goals. So for each energy case, we really have a clear scientific case for exascale simulation. That means we really develop the code with a scientific goal in head, and to really be able to do science. So basically one flagship code and sometimes satellite code. And all the technical challenge, as you can see, there are key bottleneck for several of our application, not all, but most of the time, many application. And there are also, we believe, key issue for exascale at large. And so the tools developed in this technical challenge will be useful both for our flagship application, but also for the community at large. So I won't have time to go through all our technical and scientific challenges. We'll try to give you a flavor of what we do. So for example, the work package on programming model. So we work on a performance evaluation of the code. So it's a first key issue because many people are not really aware of how well or bad their code is performing. And it's also important to monitor the performance of the code during the development to make sure while you add new physics, you keep up with the performance. We have a team dedicated to computational efficiency with Erlangen University, which has a team dedicated to that, to single node performance, because often you really concentrate on scalability, but it's also a key issue to raise the computational intensity of the code and to be able to really have the maximum single node performance. The two next points are really key, I think, for the user. So we work on application portability and flexibility to adapt the code to future architecture and to various architecture. So for us, it's really an important point because, for example, the H.P.C architecture have been changing a lot. And of course, we need code that can go to various architecture without being refactored all the time because it is huge works. And also at a given time, you often have access, for example, in the framework of PRESS or of your H.P.C to various architecture, and you want your code to be able to run on these various architecture to benefit, I would say, from all the machines that are accessible. We also work on code readability and separation of concern. So that is also an important issue. So the code, the end user are most of the time people in the physics domain, and they want to have a grasp on the code. They will use it if they feel it's their tool. So they need to be able to go into the code, eventually to change the models and to recognize their equation. And you want the code to be at the top level in terms of H.P.C, but you don't want the physics people to deal with very complex H.P.C thing like template programming or complex parallel stuff or CUDA, because most of them don't want to do that and don't have the skill to do that. So separation of concern, and I will give example, is a mean of trying to separate the layer dealing with physics, with equation, and the layer dealing with H.P.C. And doing that, trying to maintain the code, I would say, user-friendly, both for usage and for people trying to develop a new model. We are also trying to foster and to do training to develop the, and to improve H.P.C tool and promote the usage of a library because often they are very efficient. And we also work on these tools and library to make them more efficient. So, for example, things that this work package is doing with various codes. So, ALIA is a code developed at the Barcelona Supercomputing Center, which is used for many things, but we use it in the wind for energy domain. So, we have been working a lot on optimizing the single node performance of the code. We have been working on the communication. To overlap communication and computation on a GPU porting. We have done something, I think, quite original on heterogeneous cluster co-execution, that the application is running at the same time both on CPU and accelerator. So that is very useful when you have a heterogeneous system. We have done some work more technical on coupling a fixed and rotating mesh. I will show example to model rotor. and scaling curve on exascale or pre-exascale resources to try to see how the code behave at very large CPU numbers. So, for example, for the porting of Alia on a GPU, so Alia rely on linear solver. So we'll show that later. We have a very large linear algebra team. So we have been collaborating to incorporate a GPU-aware linear solver into Alia using CUDA or other library. And we have used OpenSSA for the more general aspect, the more coarse-grained aspect of the code. And we have also implemented, I mentioned that already, this co-design process. So we can use both the CPU, as you can see, and the GPU. So we dispatch the workload both on CPU and GPU to take the maximum benefit of the computing power available in a heterogeneous cluster. Then we have been working on a flow. So that's a hydrological model used for various aspects of hydrology and also of geothermal energy modeling. So the GPU porting was done in CUDA. So it's very efficient, but it's also very, I mean, most physicists are very reluctant to deal with CUDA. So as I will show later, it was hidden from the scientists using the domain-specific language. We have done AMR implementation using a library, P4est, that is very efficient, that scales very well, and that saves a lot of computing time because the grid is only refined in region of interest. And we have been working, I will show a bit more on that later, doing integration of PDI. So PDI is a parallel data interface, is a tool that we are developing in the project to make data management easier. And I will give you more detail about PDI a bit later. So just to show, that's kind of a Parflow schematic view. So the user is on the top. So they have to use a YAML input file for PDI or use an existing white, and there's a scripting language and a Parflow kind of DSL based on C and macro to really manage the high-level aspect of the code. And then the middle part is so the top part is a programming layer for H.P.C. The middle part is the programming layer for H.P.C developers, so kind of the engine of the code. So where you have a CPU backend, a GPU backend, and a new AMR backend. So these are using very specific and technical H.P.C tools, but they are totally hidden from the user through this usage of this DSL. And at the bottom, you have I would say, the programming layer for I/O expert, which are developing PDI and which allow a very efficient manipulation of data using various formats and various I/O library. And this is also totally hidden for the user. So the user is really dealing with simple C or a macro using the DSL and have access to, we say, very high-end H.P.C methodology. And one last thing, I will go fast maybe because time is running. We're also working on ARM to port the Gisela code on so we have an account on the new Fugaku machine, and we are working on porting ARM. I'm porting Gisela on ARM, and so there the issue. So Gisela was already very scalable. So the issue relies more in I would say, trying to deal with the ARM architecture and especially with the vectorization. So the processor of the Fugaku is a vector SV processor. And so we need really to optimize the vectorization of the code in order to have a good performance. So another technical challenge is linear algebra. Since I'm running out of time, I'll go fast. So we have a very large linear algebra team that is designing so both designing a linear algebra tool and implementing them in all the code. And so it's really a great asset of the project to be able to have people directly developing the linear solvers that are working with the code and trying to implement the software, the linear solver within the code. So here you have all the linear algebra package that we are using, and for each package we really have one of the main developer of the code, which is really a great help. And so we have some kind of a small matrix market. So somebody of the project can take a typical matrix out of their physical problem, and the linear algebra people can really try their solver on this matrix and see how well their solver behave. And so it allows really to pick up the best solver for a given problem. And so these people are interfacing the solver with the flagship code after choosing the best solver for this particular problem. Then they work on the solver to improve robustness and scalability. And also sometimes they design and develop application-specific solver which have a narrow usage but are very efficient on a specific and given application. I will skip this. So just a quick view on what we do on I/O and data flow. So we have developed a PDI, so parallel data interface. So the idea is that you have a many I/O library which sometimes need to be tuned to be efficient, and which are different from one platform to another. So you really need to continually upgrade your code to make the best usage of this I/O library. Sometime on a given computer, you have an I/O subsystem or a specific I/O patterns that add a new type of complexity. So the idea of a PDI is really that now you implement a PDI I/O within your code, and then PDI has backend to tackle with many different I/O libraries. So you have that at the bottom, POSIX, HD85, NetCDF, ScionLib, Melissa, and it's always extending. So it's some kind of a plugin. And you also have configuration files that really are developed for one particular system by an expert. And so that really tuned the I/O setting for this particular system. And so you couple your code to PDI, and then in your code, you have only PDI call, and then the I/O will be done using the configuration file in the best way possible for this particular system and for your need. So when you change system, you don't have anymore to deal with changing the I/O calls or trying to upgrade the I/O. And so you have many features in PDI. So instead here of really putting everything, doing a dump, if you want to do a restart or a dump for analysis of your code at one time, you can do that by taking care of asynchronous operation and dealing with the temporary storage. You can use buffer. So there are many ways you can use PDI in order to avoid the I/O bottleneck. There's also PDI can be used for resiliency, either for fault tolerance or for resiliency in large ensemble run, where you can have issues if one instance of your code is crashing down. And also PDI was designed to deal with extremely large simulation. For example, in fusion simulation with ZLR, it's a gyrokinetic code. So you have a 5D phase space, so the data are really gigantic, and you can store very few output files. So the idea, it's the blue here in the middle, is to use PDI to do online data visualization or data compression or data treatment during the simulation to store less data and more relevant data depending on the physical use you want to, on your physical case. So it's a library that was started during ECO1, and now that is being used in several applications, and that of course can be used outside the project. Just to finish just a bit on one scientific case, so wind for energy. So the scientific payload is doing a very large eddy simulation or flow over a complex terrain to test a wind farm implantation. Then we want to do that smaller scale, realistic large eddy simulation of a full rotor, and then advanced understanding of the flow physics governing the whole wind plant, because you can have you have wakes behind the windmill, and you have sometimes interaction between the various windmills. So the flagship COB, as I mentioned, is ALIA, and they want to do simulation with 10 to the 10 or 10 to the 11 grid point on unstructured grid. And you have so the issue is the optimization of turbine placement to maximize the power and reduce the maintenance, and trying to reduce the cost in wind for energy. So just to compare budget, if you can do simulation and improve by only 1% wind plant performance, it's for one wind plant, it's about 100 million saving annually. So there's really a critical issue in doing that kind of simulation. So here you have all the scales basically you would like to treat, from a global climate to see where are the wind, to mesoscale climate, and then smaller scale. So you want also to model the turbine itself, and also to model that the middle scale here, the full windmill. So I will skip this, and I will show just this way. So this is an example of a flow over complex terrain. So here you can see a topological region with a cliff, and then we model the wind arriving on that cliff, and to try to put a windmill at the top of the cliff. So the color is showing the intensity of the wind, the speed of the wind, and you can see that the flow is very turbulent. Now, most advanced models try to take into account the canopy also, the fact if you have trees or the nature of if you have high trees, it can strongly modify the way the wind is evolving. And so then you can make statistical analysis in various regions to see where it is best to put your windmill and where it would be more optimum. So this is done in a very specific place, so with a real topological information. It's not, I would say, a fake simulation. And we are also doing simulation on a much smaller scale to optimize the rotor and try to model the turbulence generated by rotors. Is that here? Yeah, I think I'm almost out of time. So we are also, I wanted to detail also the scientific challenge, water for energy, but I will go quickly. So there also we have various scales and a clear exascale ambition in this domain. And so I will conclude there. So really our goal is to build a European hub where H.P.C and energy community can meet and work on the energy transition. I think it's very important because H.P.C can be, of course, extremely useful for the energy community at large, and in many aspects of energy work, high performance simulation is needed. And also on the opposite, energy is of course a key issue, and energy can be a booster and a motivation to develop exascale system that could be needed to solve the energy issue. And we also are trying to ensure that the energy community can benefit from upcoming exascale computer. So that means developing a software that will be able to use efficiently this computer, and which are dedicated to specific energy needs. So I will stop there. Thank you very much.
Okay, Edouard, thank you very much for this thorough presentation. We have heard many of the aspects involved in the challenges around EOS theory. I'm sure we will have the opportunity to pick it up in the discussion session. We will move now to the second speaker. Before that, I wanted to remind you that through the YouTube channel on there, you can pose your questions, and then we will, Sarah and myself, we will be collecting them. You can also send any question you have for the speakers to director@cicam.org alternatively. So now we move on to the second speaker. So Gianluca, and now it's your turn.
Yeah, you should say. Can you see my screen? I don't see.
Yes, yeah, we can see it.
I don't see the sharing. Okay, but by the way, okay. So it's the first slide, yeah, because I have a dual monitor and okay. So thank you very much, Ignazio, for the introduction, and thanks for inviting me here in this CHECAM webinar. So what I'm going to say today. So here it's a rough idea of the today outline of the presentation. So what I'm going to do is, in the first part, I'm going to talk on behalf of the Andrea Beccari, that is the project coordinator of exascale for COVID. While in the second part, I'm going to talk about the origins of the exascale platform. That is the platform that is the base of the exascale for COVID project, at least from the computational point of view. And finally, I'm going to start describing some ongoing activity on this platform within the context of the project. Why I'm saying this? Because what I'm talking about is a project that started almost in April 2020. So the project is the name, the acronym exascale for COVID is Exascale Smart Platform Against Pathogens for Coronavirus. It is a project that we applied to a call, to the emergency call in February for trying to find a solution, a therapeutic solution to the coronavirus pandemic. The project started, well, it was a fast track call, so the project started immediately in April. So we can consider that we are in month 3, and the horizon of the project is a duration of 18 months. And now we are going to say why it's 18 months, because it is not only to identify, as between the objectives, not only to identify molecules that are capable to target the coronavirus, or the 2019 nCoV, but also to try to develop an effective tool for a future pandemic. So unfortunately, we know that we hope that this is the last one, but everybody knows that with high probability there will be another one after this one, another one, and again and again and again. And the peculiarity of the project is that what we want to do is to exploit as much as possible the European supercomputer facilities. This was what this is what the consortium wanted to do. So the characteristics is that the consortium, more or less, we can define that is an integrated pan-European drug discovery infrastructure. It is not only on the computational side, but we will see that has also partners that are more from the that are from the in vivo screening. So we have the base of our consortium are the 3 supercomputing centers that are Cineca, that we see the Barcelona Supercomputing Center and Jülich. But in addition to that, for the computational part, there is also Polimi, University of Milano, the Swiss Bioinformatics Institute, KTH, so the group of Eric Lindell, the Big Data Association, and the Italian National Institute of Nuclear Physics, so the INFN. In addition to that, we have partners that are related to X-ray activities, like the Electrosynchrotron Trieste and the International Institute for Molecular and Cell Biology in Poland, as well as partners that are related to the in vivo and in vitro screenings, such as the University of Naples, the University of Cagliari, Fraunhofer IME, the Catholic University of Leuven, and also the Spallanzani Hospital. So it's the Italian National Institute of Infectious Disease that was, and in particular the group that was the first one that isolated the virus in Europe. And of course, last but not least, we have to consider that Dompe Pharmaceutical is the coordinator of the interaction, and we have Kelonia that is in charge the whole communication and exploitation activities of the project. In addition to the partners, so we know that the partners are the main actors of the project. We can positively mention that we had a lot of requests from external entity to the project to contribute against the so for their research against the coronavirus, so COVID-19. And we had mainly two paths in this direction that were contributing to what we call drug box, or supporting us as an external entity, providing resources or expertise in particular field where it was needed by the consortium. So as an example, we can mention that joined immediately this external group of external collaborators that we call the League, ANI, so ANI, offering the use of H.P.C 5, so the top European supercomputer that is ranked number 5 in the last top 500. But also, as an example, IT4I, that is a Czech supercomputer, or D-Wave for offering the usage of their quantum annealer. The other that I mentioned is the other possibility was through the drug box. What is drug box? Drug box is an initiative supported by the European Commission, and in particular by the DG Connect and the FIA, so the European Federation of Pharmaceutical Company, that we use to offer the possibility to third parties to test their compound using the facilities that have been put in place by the consortium, in order to help us in finding novel drugs. The complexity and the variety of the activity planned for the project forced us to divide them into other two levels, in addition to the web packages, and then to remap the web package under those two levels, that are the field of action and task forces. So the field of actions are mainly three. So the first one, that is the basic one for the project, that is to find the action to find an effective treatment. The second one is the enhancement of the quality of the simulation, while the third one is mainly about the deployment and exploitation of the results of the project. So in the first field of action, that is of course what I mentioned before, the central one, we can find the task force about the computer-aided drug design, where we have all the activities related to the in silico simulations. Then we have the task force number 2, that include all the activities that are related to phenotypic and biochemical screening of the compounds up to the animal testing. And as you can see here, there is most of the effort of the project, as it is visible in terms of actual work packages that are related to this field of action. Then there is the second field of action, that is the enhancement of the quality of the simulation. And mainly those activities are designed to support the task force number 1 on the computer-aided drug design. So the task force number 3 is about X-ray, so the determination of the 3D structure of the viral protein, while in the task force number 4 is the one that is more related to H.P.C. So not only in terms of providing the actual computational resources where it is needed inside the consortium, but also in trying to design a scalable software platform, that is the one that we are going to talk today, for agent computing in order to select a subset of compounds to be provided then to the task force number 1. And then last but not least, there are the other 2 task forces, that is the task force number 5, the task force number 6, that are about the transition of the results from the consortium to the to EMA, and also to on the building of a broader network through dissemination and exploitation activities of the project. So what I'm not going to talk today is regarding the task force number 1. Ignacio and Sarah and all there is that we had already regarding escalate for COVID, an interesting webinar from the key person of the task force number 1. In particular, there was Andrea Beccari from Dompe and Carmine Talarico, that is the head of the task force number 1, together with Giulia Rossetti from ULIC. But also you had a lot of, at least a couple of seminars by Eric Lindell, both in the context of COVID-19 seminars and also within the H.P.C seminars. So I kindly ask you to go there if you are interested in more detail about the contribution of the task force number 1 in escalate for COVID. But what we're going to see today is something about the task force number 4, that of course is the central task force regarding my contribution to the project, and it relies on an aggregated computational power of around 60 petaflop, considering the several machines involved. If you consider the NE1, the new Cineca Marconi 100. And the goal of this task force, as mentioned before, is to support the project and all the activity of the project in terms of computing infrastructure, machine setup, network, storage, but also in optimizing and porting, in tuning the code according to the requirement of the CADD task forces. In particular, we have 2 directions. The first one is consider the protein 3D resolution. What we are going to do here is we are trying to resolve more than 20 proteins, and those 20 proteins are under processing within the H.P.C 5, the Marconi 100, to obtain a simulation of the protein of around 10 microseconds. And the result of this will be then used within the CADD task force. And second one, that is the one that is that will be the continuance of this talk, will be regarding the designing and tuning of the escalate virtual screening platform that will be used to try to provide promising compounds in a reasonable time to the CADD task force. Within the project, we envision two phases. We can call the project is composed by 2 waves. The first one is more short term. That is the first one, the one that is based on the fast track. That is a first phase that involves the screening of a library of more than 10,000 compounds. Okay, there are not so many, but those are in those 10,000 compounds are those that are already drugs into the market, or there are drugs under clinical investigation. So something that we already know that are safe in men. And this gives the possibility to have an immediate response to the to COVID-19, and of course to go afterwards to the EMA approval and clinical trials. And this is actually what's happened, as we can claim that this is the first result, the first success story, concrete success story of the project, because last month we went out with a press release where we mentioned that we found the raloxifene. The raloxifene is a drug that is already in the market, that is used for the osteoporosis, that can be used in case that is effective against COVID in case of light and medium cases of infection. But this is the first wave. So this is something that we hope to find, that we continue to find drugs that are already on the market. But there are a second phase that is the second part of the project. That is now what we want to do is to enlarge the chemical space, not only on drugs that are already on the market on in clinical investigation, but also something that is not yet with the drug head. Okay, so the idea here is to go with the very large chemical space in the order of billion or trillion of ligands, and each ligand should be docked and scored in order to be evaluated, because among those ligands we want to find only the compounds that are considered more promising, not because we want to develop a novel drug, because this is from the timing point of view is out of the scope also of exascale for COVID, but at least to provide to the community the compounds, so the results of what we did in this phase. The challenge of this second phase, it's clearly explainable in a sentence. So we have a huge number of small molecules, so as mentioned before, billion or trillion, to be screened, so to be processed in a reasonable time on the available resources. Okay, so to clarify, I inserted here a very simple equation that explains it. On the left-hand side, we have the amount of core hours that are available that we want to use. So it's the time to solution for the entire processing multiplied by the number of resources. While on the right-hand side, we have the required computational effort. Okay, so the processing time per each ligand and the size of the chemical space. So of course, we are. I'm considering that each molecule can be processed in parallel, independently from the others. But we will see that, of course, this is something that is an approximation that is more than feasible. So if we consider this, and we make to understand the dimension, we make the hypothesis to use the full Marconi 100 machine, so 1,000 nodes, and we are going to evaluate the time to solution in terms of 1 day, 7 days, 1 month, half a year, 1 year. We are going to find here on the left-hand side the throughput required for the processing time per ligand. So in particular, what we are doing, we are putting constant to the size of the chemical space. Here we are considering 1 billion. The number of available resources that is the full Marconi 100 machine from Cineca. And we are modifying the time to solution to understand what is the request. So if we want to screen 1 billion ligands inside 1 day, we need the throughput per node. Okay, not the entire the sum of all the throughput of the node, but the throughput of a node that is 10 ligands per second. Okay, then it can be relaxed to 1 ligand per second if you want to use 7 days to reach the solution. But we have to keep into consideration that up to now we are considering, so we are stopping the entire Marconi machine for one week. And the problem is even larger if we consider the target as a number, the target number of ligands that we want to screen within exascale for COVID. So that is more or less 500 billion. So we are very close to 1 trillion of molecules. So if we want a result within 1 day, if you see here that the order of magnitude of the throughput requested per node is very huge. It's in the order of between 1,000 ligands per second to 10,000 ligands per second. And of course, it reduces by increasing by relaxing the time to solution. But again, this means that we are completely considering the machine full for several days. And this number need to be compared with the state-of-the-art numbers that says that more or less the throughput for processing a ligand is in the term of second, or now we are going to increase it in the term of 10 per second or 100 ligand per second per nodes, and here there is a huge gap to be still to be solved. Okay, we are talking about processing time, but what we are referring to? So we are referring to the process that we want to tackle within exascale for COVID, that is the docking of and scoring of a molecule. So in structure-based drug design, molecular docking is the method that is used to calculate the preferred position of a small molecule, the ligand actually, when bound to a second molecule, to a larger one that is called the target. Okay. Typically, we don't talk about a second molecule in docking, but we talk about the pocket. The pocket is a particular area of the target of the second molecule of the protein that has been recognized as good for binding site. So the docking, what it does, it looks for a shape complementarity between the ligand and the pocket, and trying to fit the ligand inside the pocket. And then once it has been placed, the ligand is scored by using a scoring function to evaluate the binding affinity that is not only a geometrical binding affinity. So the idea of the molecular docking for virtual screening is in reducing the complexity of the search from a larger set of compounds to a smaller one, to then to be further investigated more in detail. And this is the base of what we are doing in within the Accelerate platform. So within the Accelerate platform and within Accelerate for COVID, we didn't start from scratch. In particular, we start from a previous European project that was called Antarex, that was a FET H.P.C. project that was not related to drug discovery, but was more on developing energy and resource efficient algorithm, enhancing the algorithm with self-functionality and with auto-tuning functionality. But within the Antarex project, one of the use cases that has been used was brought by Dompe and Cineka, and in particular, we use Ligend, that is the software, so it's the computer the CADD software used by the R&D of Dompe and co-developed by Cineka as case study. So fortunately, given the fact that the code was developed since the beginning by a collaboration with Cineka, the code was already parallel. And within Antarex, the idea that we had with Dompe and Cineka, and this is where and when we enter into the game, the idea was to bring Ligend to a next level and to try to use it for extreme scale virtual screening campaign in case of a pandemic, as what has happened 1 year later. And that's for targeting urgent computing. Okay. These are not done only considering the software, but this has been done also considering the size of the chemical space. So while we were optimizing the software on the software side, Dompe enlarged the chemical space to a larger amount of compound that could be screened by the designed platform. This was the result of the as a result, Dompe decided to demonstrate the feasibility of an experiment like this one, decide to tackle the Zika virus. So to try to envision the usage of the platform to find a therapeutic cure with, against the Zika virus. So what we did is we used the full Marconi A2 partition, so 10 petaflop LIMPAC of Cineka, with more than, by using all the 3.5 thousand nodes based on KNL to run the experiment. And this was one of the largest experiments that has been for virtual screening done up to that moment. Nowadays, we can't say any more this because with COVID, everything, the size of the experiment increased a lot. And the idea of doing this has been recognized by you as an actual success story. And just after the end of the experiment under Zika virus, Dompe launched Escalate, that is what we call the high-performance virtual screening platform that is composed by Ligend, so the previous software of Dompe, integrated with the Antarex code base, and the extension of the virtual chemical space up to 500 billion ligands. Okay, in April 2019, we were claiming that Exascale was the computational platform capable to respond to a pandemic crisis. Okay. What is the Exascale platform, and what we are doing inside the Exascale platform? Well, the Exascale platform is a platform owned by Dompé and co-developed by Cineca and Polimi. And as mentioned before, it has two main components. That is the chemical library, that are the chemical library, and Ligen. So Ligen, including the software developed within Antares. And the key element of inside the computational pipeline of Ligen, it's the module called GeoDoc, Ligen GeoDoc. What Ligen GeoDoc does? Well, GeoDoc does, it's the docking engine that there is inside Ligen for ultra-scale virtual screening, and perform a sort of relaxed lock and key model. The lock and key model for docking is the fact that you consider protein and ligands as rigid body, and you search for shape complementarity, and then you score the dock with the scoring function to rank the different ligands. We called it relaxed because then this is something that is used long time ago. But we know that the flexibility is it's a key point for having a high quality docking, and we relaxed the flexibility, so the rigid hypothesis, both on the binding side and on the ligand side. On the binding side, we do not explicitly manage the flexibility, but we use the so-called ensemble docking. So we consider multiple possible conformational state of the protein derived by long molecular dynamic simulation as a completely different binding site in the docking procedure. While on the ligand flexibility, we are more explicit, and we consider the flexibility of the ligands in terms of rotable bonds. So the rotable bonds are the bonds inside the molecule that actually give the possibility to the fragments that are linked to these rotable bonds to rotate independently one to the other one without changing the chemical properties of the molecule. And the angles of this rotation is considered as an additional degree of freedom to be considered in the docking problem. So we have the 6 degree of freedom that are the rototranslation to dock rigidly the compound within the pocket, plus we have all the degree of freedom that are based on the rotable bonds. So this is clearly an embarrassing parallel process. So that is also the reason why we call it exascale ready, because we can process each molecule in a pocket in parallel. We can process different pockets within a protein in parallel, and we can process also different proteins in different states in parallel. So that's you see that the level of parallelism is very huge, and this is also visible if we do a sort of weak scaling of Ligen doc on the Marconi 100. So this is the result that we obtained recently by scaling on more than 1/4 of the entire Marconi machine. So on 256 node Ligen doc on the Marconi machine. So you see that actually it is almost ideal, the ideal case. So the idea in this direction, the idea of having a virtual screening platform to be adopted in case of urgent computing drove also a lot the planning and development effort for today, but also for the future. The code, as you saw, it's easily parallelizable, so everything can be computed in parallel, and it has an MPI backbone. But up to this moment, it was only designed in C++. It was portable by definition because on the CPU could run without any problem. And up to last year, it was only ported on the Marconi A2 and on all the previous on Galileo and all the previous not accelerated partition in Cineca. But last year we had the possibility to access to accelerated partition, and then immediately we tried to bring the code by using OpenACC in order to exploit as much as possible also accelerated partition. Never, accelerated partition. And this is what's happened immediately when we start with xCADD for COVID, because in the meanwhile we were submitting the proposal of xCADD for COVID. Ginecta deployed the new Marconi 100 that has the same computational, the same node of Summit with the IBM Power 9 and the V100 accelerator. So we decided immediately to move from an OpenACC version of the code to a more efficient NVIDIA code, CUDA code of the docking library. This gives us the possibility to, in short term, to gain the maximum speed on the V100 card. But there is also, of course, there is also the path in the future, especially in the second half of the project, to retake care of the OpenACC version, and also on the next year, thanks to a new project that has been approved inside the Euro H.P.C call, to bring the docking code using SQL. While we are doing portability, we think about portability not only in terms of machines, but also in terms of context. Because as an example, if we consider huge virtual screening campaign, the need of processing is very high. So the throughput that we want to have is very high. But this is not the same if we consider studies or experimental campaign where the number of compounds to be processed is much limited. It's not 500 billion, as an example. And then we can have also a slower computation and maybe more accurate computation. So what we did is to try to extract from the LegendDoc application possible application software knobs that were able to tune and to find trade-off between the computation, the performance, and the degradation in terms of quality of the docking results. Let me go faster here. So what is the current status? The current status is that we have the Marconi 100 machine in production since May 2020. So Marconi machine is more or less the target that we had in this first period in order to have a large virtual screening campaign. So we started in this plot. There is the throughput in terms of ligand per second per node that we had on the Marconi machine, starting from the original KNL version, so Marconi A2 partition, and then from the second bar, it's the porting to the Marconi 100 node. So in the last 2 months, we have a rapid growth of the performance in throughput of the docking algorithm, while keeping an accuracy in the elaboration that is that is still good given the throughput rate that we want to obtain for our target. So in particular, what we did is at the beginning, we took the code that we had for the KNL and we ported on the Power 9 by using only the CPU. Then we start using the GPU, exploiting the OpenACC code that we were developing before. But then immediately we discovered that, as mentioned before, that the CUDA version, it was more easier to be managed in order to find performance. And we reach right now a throughput in terms of number of ligand per second per node that is in the order of 1,500 ligand per second. That is an order of magnitude higher than what we had before. Let me skip a bit here. And before concluding, so to obtain a further optimizations, to increase more the throughput of our docking, we also decide to apply trans-precision technique. So the idea is to actually use the max accuracy only when it's needed. So geodoc actually was ported to the GPU using the original 64-bit precision, so the double precision. So this was the original one. But then what we did is we considered the several phases and the several kernel of that are included inside geodoc, and we tried to understand when and what were the kernels that impacted less on the output precision. And after several tests, we verified that it was possible to reduce the accuracy in some of the kernel, and in particular, passing some of the kernel from a double precision to a single precision, obtaining a significant speed up on the GPU, while this speed up was almost not visible on the CPU side, and this was the reason why it was not faced before. And that it is visible here in this graph that shows the trend of the throughput in terms of ligand per second per node that we have on the Marconi machine, on the Marconi node. It's possible to see that nowadays we are around 1,800 ligand per second, close to 2,000 ligand per second for the screening side. That we are very close to the limit that to the goal that we were planning at the beginning of the project. So last but not least, if you remember what were the escalate for COVID goals, the first objective was to identify a molecule capable of targeting the coronavirus. So we already, as a consortium, not by using Escalate, we were able to find the relaxofen molecule. But also the idea is to develop an effective tool to countering future pandemic, and to consolidate, to have this tool consolidated over the time. And this is more, and this is much more important for the platform that we are designing, especially because we hope that the Escalate platform can be the computational platform dedicated to addressing next pandemic crisis, considering the goals of scalability, configurability, and portability that we placed, that we decide to have for the software. So the work that I presented here is, of course, not only by me. Here there are the other members of the Escalate development team. On the right-hand side, there is my team in Polimi, considering Davide Gadioli, Emanuele Vitali, and Professor Cristina Silvano. There is the team in Cineca that is composed by Chiara Latini, Federico Ficarelli, and even if it is not more in Cineca, but it is one of the head of the development team before, that is Carlo Cavazzoni. And on the left-hand side, we have the team inside Dompe that supervise the development of the platform. So you can see here that there is Andrea Beccari, that is the coordinator of Escalate for COVID, Candida Manelfi, and Carmine Tallarico. So I hope to give you a good picture about the project. So that's all from my side.
Thank you, Gianluca, and thank you again also to Eduard. So we're now ready to move to the Q&A part of this webinar. We have one question from our viewers so far. So let me start by encouraging everybody to ask more questions. If you want, you can do this using our chat, log in on YouTube and then just type your question, or by sending a question to director@ccam.org. As usual, what we try to do in this part is to have a discussion that tries to bring together a bit the different types of applications that we've heard of from our speakers. I would also ask the speakers to think, if they want, about questions that they'd like to ask each other, because I understand that you come from very different fields of applications, but the H.P.C component of your work is certainly something that you have in common. So, okay, let's start from the first question, which is the question from our viewers. This is a very specific question for Eduard. I guess your linear algebra efforts have intrigued at least Fabio Affinito from Cineca. So the question is, in the linear algebra constellation, I don't see something for dense large matrix problems, something similar to Scalapack, for example. And he would like you to comment on that. Is there a specific reason why this is absent?
Well, I don't know exactly all the linear algebra package by heart. So, I mean, if he knows this, probably right. but very large dense matrix are not very useful for our project because we are dealing, most of the matrix come from PDs. And so basically one cell is interacting with neighboring cells and not with all the cells. So most of the matrix we are dealing with are sparse matrix. And so not all the work we are doing is on sparse matrix, and which are less computationally intensive and require are more tricky concerning memory access. So we are working on sparse matrix and not on a dense matrix.
Okay, I actually also had a curiosity about this work on linear algebra solvers, because I didn't quite understand how transferable or portable the work that you're doing for specific codes is going to be. Maybe this is not your primary interest. My understanding is that you really target the flagship codes and the specific applications that you want to, but is there any plan, for example, to turn these solvers into a library that could be accessed by the community? Maybe I missed it if you said it, sorry.
No, most of the package are already library. We have MENT, we have AGMG, so most of them are already library, which are quite popular and accessible to the community. So the advantage that we have is that we have the developer of the library, so he can really help to, I would say, to tune the library for a given application, to interface it properly, and to make the most out of the library. And sometimes a specific development are made for a given application, but they are put back into the production version of the library, so they would be used by other people later on.
Okay, thank you. Sorry, I missed that bit. A little bit on the same theme, Gianluca, because I was very, very impressed by the amount of work done by Escalate for COVID in such a short amount of time. We know, of course, that there are many efforts in the communities, in particular in the computational community in Europe and also in the US at the moment. And I was just wondering how you would place your project in this broader landscape, and in particular, collaborations, joining efforts, avoid duplication of efforts. Can you comment maybe a little bit on this?
Well, yeah. So I mean, the first comment is about the amount of work done in so short time. So as you can imagine, it's there is also well, a pressure from outside, but also from inside to try to find a solution. So that is the one of the points. So we also, even if the project started in the officially in April, already most of the partners started working on it at the beginning of February. So everything was started to be in place in that moment. So even if as an example, also for our side, even if the Marconi machine was not yet available, because actually it went in production in May. So it's and there was not anymore the Marconi A2 partition, so the kernel partition. So we had a sort of a black period where we didn't have any access to a large machine. But in any case, there were the other partitioning that were working, and we did a lot of work in the meanwhile as well. And well, with respect to the other efforts that are around the world, yes, I want to say that of course our effort is particular. So it's the one of the European effort in using supercomputing. One of the points is that we are using and not an open code. It's a code that is owned by Dompe. So this is one of the limitation in sharing also the development effort that we have. But especially the CADD team, so the task force on CADD and Andrea Beccari, it's sharing the findings and is sharing the effort together with teams that are working also abroad. So there is a link also forced by the European Commission among all the dedicated effort inside Europe, but also to share effort and to try to coordinate the effort with outside the EU, in particular with US.
And what kind of data is shared? Do you know that? I mean, are structures or specific proteins on the virus?
Yeah. As I mentioned, one of the largest effort that we are having, it's in resolving the 3D structure of the protein, and the 3D structure of the protein is something that has been made available to the community. So continuously there are updates on the data that are produced by the consortium. So this is for sharing. This is also forced by the European Commission, because this was one of the constraints during the call, that everything that is found within the project, all the results of the project, should be made public within 1 month after the findings. So this is something that is the project want to share, but also it's something that Europe want, that the effort or the money that they are putting on the plate are also not only related to the consortium, but also for the entire community.
So we have another question that is related to the virtual screening problem, and that is, given that you must read and write very many files, do you find that there is an input-output problem?
Well, the answer was I didn't mention this, but originally during the Zika, the Antares for Zika experiment, yes, there was a problem on the a problem on the I/O. So this was a bit the limiting factor on that experiment. So we were the computational side was almost okay, but when we scale up to a certain number of nodes, so the entire machine, the I/O the I/O problem started going out. However, the problem there was also due to the fact that experiment was also done to test that everything was properly working. So we were not only dumping a sort of scoring of a molecule, but we were dumping several positions, poses of the molecule inside the pocket. So that this requires, especially in writing, much more bandwidth than writing only the score of the molecule, and then only later to retake the molecule that are higher ranking, and then to redock again. And this second type of processing is the one that we are planning for the large experiment inside exascale for COVID. So there is a lot of attention on the I/O given our previous experience, but we don't think that nowadays we are going to have the problem. Indeed, the graph that I showed you about before about the weak scaling was actually demonstrating that there is an almost linear scale with respect to the number of nodes. So the I/O up to 1/4 of the size of the entire Marconi machine was not the problem on the I/O were not yet there.
Okay, thank you. Ignacio, do you have a question for our speakers?
Well, I mean, yes, certainly. In following up with this virtual screening, Gianluca, you mentioned, you have emphasized the need of really addressing the speed, the time in which you can provide an answer, and how to develop a computational strategy around it. How did you address that issue? You were talking about this balance between having a fast or a slow campaign, and more. How much does it go into structuring or determining how you want to go through chemical space, and how much it's into the docking or the developing of codes or the reorganization of the structure of the algorithm itself?
Ignacio, can I ask you to repeat the question, because I don't know if it is a problem on my side or.
Okay, I was thinking, well, it's a question of how the different aspects associated to having to face this challenge of having a computational campaign that is fast enough. How did you address in terms of how to balance fast versus slow, and to which extent it's more about, or in your case, it was mostly a question of identifying how to choose compounds or how to rewrite the codes or how to adapt them to these new architectures that you were describing?
Yeah, I mean, we tackled the problem, I mean, by using three main paths. The first one was, okay, there is a new architecture. So we knew that the code was could have advantage of GPUs. So we could imagine that we could have a huge speed up by porting it on the NVIDIA V100 card. So this was the first step. So the first step that we did is to go towards the porting of the previous code. So of course, the idea that we had, since we want to have something ready in very short time. So I think that by the end of the month, we would like to have the large experiment, or in the next 2 months maximum, we want to have the large experiment. We could not redesign everything from scratch. Okay, so the idea was to start with the previous code of Lygen and to port Lygen on CUDA. And for targeting the V100 card. The second part was to trying to optimize as much as possible the computation that there was inside the docking algorithm, by trying to skip the computation where it is not needed, because this is the fourth point, and to try to use the accuracy, the right accuracy, depending on the step of the computation that you are doing. So to try to find in all the computational process the sweet spot for that particular kernel. And this is very important, because without finding those sweet spots, it was impossible to have this huge increment in terms of throughput. Indeed, I skipped the slide because of the time, but what we are doing right now is to try to find a way to fine-grain tune the computation of each single molecule according to the specific structure of the molecule. So the configuration, the coarse-grained configuration that we can have in order to decide, okay, I want to screen this database in a certain time, can be further refined, considering that each molecule are its own particular structure. So the position of the rotable bonds, so the number of rotable bonds, the number of atoms that are inside the rigid structure of the molecule are a characteristic that we are using in order to fine-grain tune the particular processing of the single molecule. So this is the other point that we have. But then there is the third one. So it's what if we are not able to reach enough processing time, because now, I mean, we are almost okay for 500 billion, but what about 1 trillion or 2 trillion? So what's happening if tomorrow Andrea Beccari from Dompe comes with a database that is even larger than before? Yeah, of course, we are also trying to evaluate alternative solution. As an example, is currently not part of the XCADD for COVID, but the support of artificial intelligence, at least to pre-screen some molecules, or to put a priority to the molecules inside the database, is something that we are trying to face by adopting classical technique like recommender systems. It's one of the possibility that we are trying to face, and this is exactly one of the support that we are having externally from the consortium, from IT for Innovation, so the Czech Supercomputing Center.
Thank you. I also have a question for Edouard. You see, in your, I mean, your CEO, I mean, you haven't been explaining the effort on these codes that you identify where you do work to adapt them to scale in this new H.P.C architecture. But on the other hand, you were referring both to the fact that then you have scientists wanted to bring in more physics, and also a little bit this tension between the users who are scientists or engineers that need to exploit these new codes or the new version of the codes, and the complexity of coding them. So how do you see that interaction, or how within the EOCOE, which decisions, or how you think it can be in the future a good way to handle these two different aspects around codes that become more and more complex in themselves, and also because of the landscape or the infrastructure in which they have to run? So I think you.
Sorry, I was
you
muted.
just-
Yeah. I think it's a very important issue for exascale, because first of all, some people want to scale their code to do the same thing with a higher resolution or more time step. But in many cases, you also want to do more complex model with more physics. So it means that the physics people, when I say physics, it's the application people. It doesn't have to be physics. Really want to have a grasp on their code and be able to look within the code, and they need to do that. And most of the time, they are not H.P.C expert. And then on the other side, if you really want to use H.P.C, I mean, very large machine in the best possible way, then you really need to do things for programming, using programming technique and programming models that are extremely complex. And otherwise you will not make it. So the idea is really to work on this separation of concerns, that is trying to have a hidden part of the code that are not managed by physics people, and to have the physical layer of top. And I mean, it doesn't always work, but it, I mean, separation of concern is kind of a nice dream, and it doesn't always work, but you can in some, I mean, sometimes you really have tools that allow you to do that in quite an efficient way. And I mean, it's not perfect, but it makes things better. And so you can both have with a high-end staff and keep a code, I would say, readable for people. And then we develop the usage of library also. I think library are often very highly optimized and can be used by codes, so they benefit from the optimization done in the library, and the effort is not so much. I mean, you benefit from work of other people, and so that's both the way using library and trying to work on this separation of concern, and also trying to teach the community and try to raise the H.P.C awareness of people in the community is another issue. And the last issue also is probably with code portability and code development on the long run, because people want their code to be flexible and to run on various architecture. So I say we have portability across platform at a given time, and they also want their investment to last for a long time. So as much as it is possible, you want to try to do things in a way that your code should be compatible with the future architecture, which is, I mean, things have been moving very fast lately in the domain of hardware for H.P.C, so it's not always something easy to do.
Thank you, Eduardo. So we have received one question via email for Gianluca from Rosa Di Felice. It's a multiple part question. So I would suggest that maybe I can forward the email to you, Gianluca, and you can be in touch with her. There is one part of the question that I find intriguing, because she was curious about the fact that you mentioned D-Wave. And so the question is, are you implementing a docking scheme on a quantum computer, or is this something that you have in mind for the future? Do you see this as a realistic option?
Well, this is something that we are actually, I mean, it's a try that we are trying with the people that works on quantum in Cineca. So well, right now it's not actually docking. So it's something very similar. So that try to manipulate the degree of freedom of the molecules. So what we're trying to do is to generate the Hubo and the Kubo problem for the D wave on the fly, given the structure of the molecule, and trying to find the the position of the molecule that optimize a certain scoring function. Not yet the actual docking. So there is not the second molecule. So it's the first try that we are doing. And yes, of course, it's more for the future. even if there is one step that is the molecular expansion, that is one of the steps that we have inside the docking procedure that there is inside LeadGen that we would like to implement by using the D-Wave and the quantum computer. Yeah.
Thank you. It was, yeah, the question was if you were doing quantum annealing, which I think is closer to your answer actually. So Eduardo, I would like maybe to ask you one final question, because you mentioned work in the domain of materials, but then that wasn't, those weren't the case studies that you chose for today. And so I was curious if you could tell us a little bit about that kind of work within.
So in the term of that, we have two very specific topics. So one is working on solar cells. And then we have two. So we have a team working on modeling a perovskite for solar cells at the University of Bath. And then we are working on a solar heterojunction also for solar cells. So that's the two domains where we work in solar cells. And we have another team working on battery and supercapacitors. So it's a different topic. So to try to model battery, and we are trying to couple a quantum Monte Carlo code to higher level codes, and especially to try to put constraints on functional in DFT using a quantum calculation.
Thank you. Are there questions from the panel? Others? Ignacio, I don't know if you have other questions, but you, Gianluca or Eduardo? If not, I think that we are approaching 5 o'clock, even with 2 speakers. So maybe it's time to wrap things up. Ignacio, I leave you the floor.
Yeah, I don't know if you can hear me. I saw that I frozen. Don't know why, but anyway, I should finish by thanking Eduardo and Gianluca for these very engaging presentations and for the nice discussion around the challenges that you are facing and the initiatives that you have started. I'm sure this will be interesting for a broad community. And for the people who have been following us, thank you very much for also following this fourth session. And I invite you to next Thursday, where we will hold the last session of this webinar series. So I hope see you all then. Thank you very much and good afternoon. Bye.
Bye.
Bye. Thank you very much.
Bye-bye. Thank you very much.
Are you still online? No. Sarah?